Well, hi there. Let me say a few words about well logs in geology. Among the many things geological scientists do is to work with well logs. I will show you a quick application of this type of work. Now, to quickly introduce myself, my name is Robert Font. I have a PhD from Texas A&M University. I'm a former professor at Baylor University, a former project supervisor and area geologist for what is now ConocoPhillips. I'm the former president and owner of GDM. I'm also a certified professional geologist as recognized both in the US and Europe, and an active member of the AIPG. Now you may ask, what are well logs and what do we use them for? Well logs are records of the rocks through which the well has been drilled. They are also a record versus depth of the physical and chemical properties of the rock units that have been penetrated. We use well logs to correlate subsurface formations, to determine rock properties, electrical properties, acoustic properties, natural radioactivity, the density of the rocks, etc. Also porosity and permeability and the type of fluids that are contained in the rocks, as well as the structural attitude of the formations. Interpreting well logs takes a special training and experience. Let's look at two different rock units. The top one that you see on the log is a 12-foot zone from a depth of 6760 to 6772. The bottom one is another 12-foot zone that goes from 6818 to 6830. The red arrows point to the spontaneous potential, or the SP curve. The SP curve distinguishes between zones of little to no permeability to those that are more permeable, where the SP curve actually swings to the left. Both porosity and permeability are needed to allow fluids to flow through the rock formations and to allow the recovery of these fluids. Porosity has to do with the open space or void space, and permeability has to do with the interconnected pore space. The vertical red line that is shown on the log is a baseline showing zones of no permeability. These are typically clay-rich zones. These are the lowest readings recorded by the SP curve. The green arrows shown on the log point to the electrical resistivity curves. Electrical resistivity is the reciprocal of the electrical conductivity. High resistivity may be indicative of the presence of fluids such as oil and gas, or they could indicate tight or dense formations. The light blue arrows point to the gamma ray curve, which measures the natural radioactivity of the rock units. The gamma ray curve tends to mimic the SP curves, swinging to the left in more permeable zones. Gamma ray readings are higher in clay-rich shales than in the reservoir-type rocks such as sandstone and limestone. The orange arrows point to a quick-look curve that we call the RWA curve. In zones that are saltwater wet, the RWA curve tends to swing to the left of the SP curve, or it may track it. In zones that contain oil or gas, the RWA curve swings to the right of the SP curve and shows significant separation. Based on what I said, it appears that zone 1 is water wet, while zone 2 appears to be oil bearing. And here's a close-up of the oil bearing zone. Notice a significant separation between the SP curve indicated by the red arrow and the RWA curve indicated by the orange arrow. Also notice how the SP curve swings to the left while the RWA curve swings to the right. The zone, by the way, proved to be an oil-saturated sandy conglomerate and a productive reservoir of limited aerial extent. Well, I hope this proved helpful. So goodbye and good luck.